Good afternoon. So let us start. Unless there are questions on previous things, curiosities, things that you would like to see again before we start a new chapter of our story. No. So okay. So today, oops. The line is okay. I know what it is. So time independent perturbation theory. Okay, so this will be the subject of the next 2 or 3 lectures. So to repeat, suppose that you know how to solve a certain Hamiltonian, which we will call from now on H0. So you know everything. You know, for instance, the eigenstates, okay, of this Hamiltonian. You know the eigenvalues. And in order to distinguish those quantities for H0 from other quantities that we will introduce in the following, let us label them here with the 0, okay? It means the solution of H0. Just to be definite, H0 might be the harmonic oscillator, the hydrogen problem, whatever problem you have already solved and you know to solve and calculate all the eigenstates and so forth, okay? Now, I give you the following problem, H0 plus some lambda v, okay, some perturbation, okay? So for instance, in the harmonic oscillator could be some x cubed or some x to the 4th potential. In the hydrogen atom could be, for instance, the spin orbit coupling term, okay, or any other perturbation. I put a lambda in front of it because this is a parameter that indeed I will put to 1 in the end. So it's a parameter that I can vary from 0 to 1, okay, and it gives me the order of perturbation theory in a very simple way. So I want to find the solutions, the eigenstates of this problem. So new states phi n of lambda equal to some energies, which in general depend on lambda, phi n lambda, okay? Notice I keep using n as a label. Once again, in the hydrogen atom, it would be more than 1 index, okay? And in general, it's a label. So, but it's useful just to keep it general in this way. Obviously, in the limit lambda going to 0, you expect that this should go to this, okay? And this should go to that. So we expect that in some sense, we should be able to perhaps expand these states and these energies in terms of simpler things, okay? So set up some expansion, some systematic way of expanding the new solutions that we want. Okay, now, in practice, sometimes this means diagonalizing matrices. Why is that? You know that once I select a basis, for instance, I could use this as a basis for my Hilbert space. Then once I select the matrix, the basis, every operator, for instance, this operator, is a matrix, and every vector is, every state is a vector. Let us do this explicitly. So this means, for instance, that if I calculate the matrix element of this, I insert an identity here in the form of the sum over, let me call it M, of phi M0, phi M0, okay? And I also insert an identity there, okay? And there. All in all, what you have is the following, that the matrix element of H0 plus V between the state phi 0 m, okay, and phi 0 m phi n of lambda, okay, summed over n. Well, with the first identity only, I would write it like this. Okay? This by just inserting an identity. Now, if I want to, I'll still write this as a matrix vector product. I need another element here. And you realize that every component, okay, should match. So perhaps I should call this M prime. Okay? And I realize that phi 0 m H0 plus lambda V phi 0 m prime phi 0 m prime phi n lambda summed over m prime should be equal to E n lambda phi 0 m phi n lambda. Okay? Now you see this is a matrix. Okay? Let's call it H0 plus lambda V m prime in the basis of my original eigenstates multiplied by the vector representing the phi n in the basis. Okay? So the phi n component m prime, okay, summed, equal to some energy times the vector phi n component m. Okay? So the problem is to find new eigenvectors of these matrices, okay, of this matrix, and corresponding new eigenvalue En. All right? I hope this is in principle what you should do. Is this clear? In terms of, in the basis of the old ones, right? Yes. Yeah. Okay. Is this expression clear? I mean, I got it from here by just taking, for instance, the matrix element with phi 0 m. Okay? You see? By projecting on a given basics element phi 0 m, what I got is this. And inserting the identity there. This is just a way of rewriting this abstract eigenvalue problem into a practical matrix eigenvalue problem. Okay? So the new eigenvalues and the new eigenvectors are just the standard eigenvalue eigenvectors of this matrix. Okay? Now, you see that this is in general a matrix which is full of numbers. I mean, let us write this matrix. H0 is very simple. Okay? So I write the matrix H0 plus lambda V in the old basis. So M prime. Okay? So to be definite, this thing. Okay. So H0 is simple. It's simply a delta. It's the value of the, for instance, E0 of the first state, E0 of the second state. Okay? It's a diagonal part of this thing because these are eigenvectors of H0. But this is in general making the matrix fully non-diagonal. So for instance, here I would have lambda V1, 2. Okay, let me use a shorthand. V1, 2 means the matrix element of V between the state 1 and the state 2. Okay? And similarly here I have lambda V1, 3. Okay? in principle, I might have here also plus lambda v11, okay, which is the matrix element in the diagonal. In principle, this is there as well, okay? And here I would have plus lambda v22, and then I have here lambda v23, okay? Is this clear? Lambda v21. It's full of numbers, okay? So I have to diagonalize this new matrix. So let us, and I assume that lambda is not large. If lambda is large, forget about trying to solve the problem. But I assume that lambda is reasonably small, or better, lambda v is really small, because in the end, lambda is just a parameter to get the order of perturbation, but v has to be small, okay? What? This is a vector. No, before. Here. Yeah, I think this is a cat. It's like a product scalar. It is, well, it is a matrix times vector product. Which one? Here. There is nothing there. But there is, if there is nothing here, there is nothing there. I can put a phi m, and then I put it there as well. Okay? So this is obtained from this by just projecting on a given phi m. And now it's more clear that this is a matrix vector problem. Okay? So a standard matrix eigenvalue problem. Okay? So let us consider, to start having some ideas, a simpler problem. So suppose that your Hilbert space, rather than being infinite, as it is in general, okay, and indeed the labels might be even not discrete sometimes, so you should imagine this as a, in principle, a kind of horrendous matrix. Now let us suppose that you have a 2 by 2 Hilbert space that you would like to solve, okay? So the matrix that I was talking about before now is something like, let's see, is something like E01 plus lambda V11. Then I have lambda V12, lambda V21, E02 plus lambda V22. Okay? So this will be our warm-up exercise. Okay? Rather than diagonalizing the infinite huge matrix, we do it 2 by 2. Okay. Now, to diagonalize this matrix, so to solve for the new eigenvalues, what I should do is to calculate the determinant of the matrix you see there, okay, let us call it M, minus E times the identity, okay, and search for the values of E that make the determinant equal to 0, okay? This, by definition, is the eigenvalues problem, okay? So what I should do is to calculate this minus E, and calculate the determinant and find the solution for E. The problem is obviously quadratic in E because it's two-dimensional. Therefore, you will get two solutions. Just to simplify, it's like having, say, let me call this A11. This is A22. This is A12, and this is A21, which is, by the way, the star of that, okay? Because this operator is Hermitian, and therefore the matrix element of the transpose is equal to the star. Okay? So this is just the star of that element. 1, 2, star. So minus E. How do you solve this problem? Well, it's A11 minus E times A22 minus E minus A12 square, which should be set equal to 0. And you see immediately that this is equal to, well, you know this, how to do this calculation, right? I probably shouldn't waste time saying that the two, I just go to the solution. There are two solutions here, and they are essentially given by the semi-sum of this element plus or minus the square root of the difference between the two, semi-difference, so A22 minus A11 divided by 2 square plus A12 modulo square. Okay? So you can see immediately this. Okay? Good. So let us plug this for A11, this for A22, this for A12, and the star. Okay? So you immediately see that you have something like, let me write it here. You have E02 plus lambda V22 plus E01 plus lambda V11 divided by 2 plus or minus the square root of the difference now between these two things. So E02 plus lambda V22 minus E01 minus lambda V11 divided by 2 square plus lambda square V12 modulo square. Okay? These are the two new solutions. I would like to understand what happens for small lambda, because after all, I am assuming that I want to do perturbation theory in the potential, and therefore in powers of lambda. So let us start assuming that the two eigenvalues are non-degenerate to start with. Okay? So non-degeneracy means non-degeneracy eigenvalues means that E02 is different from E01, and in particular, I can always assume that it is big. Okay? So not equal. Now, you see that if this is not equal to this, this is some quantity, which is different from 0 in general, which I can take out, okay, of the square root in a reasonably simple way. Okay, let me erase a few things. I need some space. I think I will just use this part. Okay. So I will write the two eigenvalues as the semi-sum. So the first line, E02 plus lambda V22 plus E01 plus lambda V11 divided by 2. Then I have a plus or minus E02 plus lambda V22, now minus E01 plus lambda V11, okay, divided by 2. Times the square root of 1 plus, okay, this is this thing I've taken it outside, and so it becomes now a 1. E02 is greater than E01, so I write in with this sign, okay, plus lambda square V12 square divided by the square of this, so times 4 E02 plus lambda V22 minus E01 plus lambda V11 square. Is this clear to everybody? I've just done very, very trivial algebra from the solution of the 2 by 2 problem. The reason why I do that is because I now want to expand in lambda, okay? And the square roots are easily expanded when I have 1 plus some small parameter. you realize that this starts with lambda square, okay? Indeed, lambda appears in the denominator as well. So I might expand this thing in lambda to get further correction. But to order lambda square, you can even set these two things to 0, okay? You realize this? This is already lambda square, okay? So the lambda square term is given by what you see there times just the difference of energy squared, okay? Then there are plus other terms, right, here. But the lambda square is just very, very simple, okay? So let us see. These are all linear in lambda, okay? So I need to do, yeah. Okay, yes. I want to be explicit on this. The next thing I will do is to expand the square root. But you see that the square root is not just 1 plus lambda square. There is a lambda in the denominator, okay? So in principle, that thing is 1 plus lambda square, which multiplies 4, 1, 2 square, divided by, let's see, I have E0, 2 minus E0, 1, okay, plus lambda V22 minus V11, and the whole thing is squared, okay? So let me take this out and write this as 1 plus lambda E0, 2 minus E0, 1, and obviously I need to do nothing, okay, like that. Clear? I just wrote this as 1 plus lambda because that's the usual way you expand easily things. So immediately realize that this quantity here is square root of 1 plus lambda square 4V12 square divided by the difference in energy squared, multiplied, if I expand this is 1 plus 2 lambda, then I expand 1 over 1 plus 2 lambda something, and this is roughly 1 minus 2 the something, right? Okay? So this thing here gives me an extra factor, 1 minus 2 lambda, okay? Where this dots are just this. Clear? So you see that the order lambda square is just this, okay? Just the 1. So it's like putting lambda equal to 0 in the denominator. And if I want the lambda cube, obviously I have to account also for the corrections in the denominator, okay? But then when I expand, I have the square root of 1 plus the something small. It's equal to 1 plus 1/2 the small thing, okay? Plus corrections, okay? This is the expansion now of the square root that I'm trying to do. All right? If I want to keep only the smallest correction, remember this is lambda square plus lambda cube plus blah, blah, blah. So the smaller correction, I can simply consider the lambda square, okay? So the smallest correction here is simply 1 plus 1/2 whatever I had there for lambda square. So to summarize, this thing would be just equal to 1 plus 1/2 lambda square for V12 square divided by the difference in the two energies squared plus smaller things, okay? Hopefully this is clear to everybody. So in a sense, I got rid of the square root, and I have some perturbation there. Okay, so let us go back to our original expression. This is still exact at this level, but now I have expanded this. So the solution is 2 eigenvalues. One, okay, so let me do it. So you see this square root starts with the 1, okay? So the 1 really, I can take these two things, and you see that I have, for instance, what is the best way of writing? Oh. Let us just write everything, okay? Otherwise, I think I will. Okay, so this is over 2 plus or minus the same thing here. So E02 plus lambda V22 minus E01 plus lambda V11 divided by 2, which multiplies 1 plus this thing. So the 4 and 2 is just 2. Then I have lambda square V12 modulo square divided by E02 minus E01 squared. Okay? Let's see if we agree with this up to this point. Okay. Very good. So let us see. This is a positive quantity, okay? So the smallest eigenvalue is given by when you take the minus, okay? So E minus will be our smallest eigenvalue. Let's calculate. I take the minus here, so I see that this and this piece, okay, remember there is a plus, a 1 here, so this and this cancel, while this and that sum together, okay? So it is equal to E01 plus lambda V11, okay, from the 1. But now I have also to include this minus this thing here, okay? And you see immediately that I have the 2 and the 2 there. So I have minus. The 2 and the 2 cancels. I have lambda square, V12 square. Then I have, from here, it's enough, if I want the lambda square term, which is dictated by this, it's enough again to take here lambda equal to 0. In other words, to drop these two terms, okay? Because this would give me a correction to order lambda cube, okay? So if I want just lambda square, I can take just here E02 minus E01. The 2 is gone. And here I have another E02 minus E01 squared. Okay? So this really drops one of the denominators. Okay? So result is, just to summarize here, that E minus is equal to E01 plus lambda V11 minus lambda square V12 square divided by E02 minus E01. Okay? Let us calculate the other. So E plus. In this case, I do have here to take the plus sign. So I see that the minus, the 1 cancel now, this 1, but the 2 sum together and give me E02 plus lambda V22. And then I have to account for this, and I get a plus instead of a minus. I get the usual lambda square V12 square. The 2 and this 2 here cancel. Same reasoning as before. I can neglect the lambda coming from here. And same reasoning as before. This factor cancels one of these two things. So I just have the same expression, minus E01. Okay? So the E plus is E01 plus lambda, sorry, E02, V22 plus lambda square V12 divided by E02 minus E01. Okay? Plus things. Okay? So these are this expansion to the smallest two orders in lambda. You see, lambda is really, every time there is a lambda, there is a v. No surprise, okay? So this is linear in v, okay? This is quadratic in v, and indeed quadratic. Now, this is, yeah.
When we expand the denominator, do we assume something? Because we have 1 plus lambda over E2 minus E1. And, okay, lambda V1, V22 minus V11 over E2 minus E1. If the difference in the energy, I mean, if it is small, then, okay.
No, the difference is finite, okay? E2 minus E1 is finite. As long as it's finite, you can always take lambda small enough that everything else is smaller than this, okay? In some sense, this is telling you the following thing. This is telling you that there is a smaller level, E01, separated by a larger level, E02, here. As I turn on lambda, there are two effects. First of all, V might have a non-negligible, I mean, a non-zero matrix element average in the state, okay? This is, after all, the unperturbed state, okay? Matrix element of the perturbation, okay? If you remember what this is phi 0, 1, V, phi 0, 1, okay? It means take the perturbation and calculate the expectation value on the unperturbed state 1. Okay? So if this is different from 0, it means that this thing will start increase linearly, and this thing will start increase linearly, in general with two different slopes given by these two little matrix elements. But the nice thing is that there is also a square term that is opposite in the two. For the ground state, you see that everything here is positive. E2 minus E1 is positive. Okay, so the ground state tends to be shifted down, while the excited state tends to be shifted up by the square term. Okay? Obviously, once this linear and quadratic term grow big enough that, I mean, this thing is almost closed, you shouldn't rely any longer to this. Okay? So, as long as these are small corrections to the initial eigenvalues, you believe them. When they start to grow big, then you should worry about what happens to order lambda cube, lambda to the fourth, and so forth. Okay? So this allows you to calculate small shift, okay, of non-degenerate in the sense that the two eigenvalues are separate. Okay? Good. In a while, we will rederive those formulas to second order and perturbation theory in more general ways. Okay? So not from a 2x2 problem, but for a general problem. One other thing that we can still extract from the 2x2 example is, what about if the two eigenvalues are exactly the same? Okay, so this 1 and 2 coincide. Okay, if 1 and 2 coincide, in general, you shouldn't do what I have done here. For instance, here you see I have a 0 in the denominator, so I should not take this away. And rather than doing this, in fact, consider that if 1 and 2 are the same, okay, so let us write this again in the original way. Okay, so this is inside. Okay, this is inside, and here there is a square. Okay, so if 2 and 1 are the same, this drops. And this is just the same thing. So let me write it again here. So this is equal to E0 plus E1 over 2, so E0, 1, the single eigenvalue, plus lambda V22 plus V11 over 2, plus or minus. You see that now lambda is in front of everything. So I can take lambda out. So this is lambda times the square root of V22 minus V11 over 2 square plus V12 square. Okay? So this is still exact now. I haven't expanded anything. And you see that there is no need to expand anything. Okay? So I know exactly the two eigenvalues, okay, to order lambda are just given by, so at the beginning they were degenerate, E01 and E02 are degenerate. Now they are split. And notice they are split linearly in lambda, okay? Contrary to the plus or minus thing that before were quadratic. Now they are linearly split, okay? And what you see is that essentially they are split by the, what matters is the eigenvalues, eigenvectors of V, okay? You see that this is like having diagonalized V. After all, if these two things are the same, this matrix is nothing but a matrix E01 times the identity plus the matrix lambda multiplying the matrix for V. You see? I can take lambda out. Which means that the 2x2 problem you have to solve is simply to diagonalize V rather than diagonalize E0 plus V. Okay? And diagonalize V gives you two eigenvalues in general, which are given by this formula. Okay? The semi-sum of the two plus the square root of the semi-difference plus, okay? So the two eigenvalues of V will just give me this very simple linear shift. Now, this case is called degenerate perturbation theory. The other case is the non-degenerate perturbation theory case. Now, depending on the problem, sometimes we will encounter non-degenerate perturbation theory cases. For instance, I don't know, in the case of the harmonic oscillator perturbations, all the states are non-degenerate, and you keep studying with that formula or the generalization of those formulas. In the case of the hydrogen atom, we will often need this, okay? Because, for instance, all the p states are degenerate, okay? So what the spin orbit does to this degenerate manifold? Well, what the prescription of perturbation theory will be is to diagonalize the perturbation inside the small subspace, okay, of degenerate state. This will give us the splitting to linear order in the perturbation parameter, okay? So we'll learn these things in due course, okay? So hopefully this 2x2 simple exercise gives you a picture of what is going to happen in the more general case. All right, so let us, if there are no questions, let us start with a more general setup. rather than, so I write the problem now again in abstract form rather than in matrix, because otherwise the calculation would be very complicated. So what I have is the following: H0 plus lambda V times phi n of lambda should be equal to En of lambda times phi n of lambda. Okay? So let me assume that this object here has some expansion, and similarly this has some expansion. So let's see. This should be what? The unperturbed state, okay, when lambda is equal to 0, plus lambda, first order expansion, times some other state, which I don't know, and I call it phi 1, plus lambda square, some other state, some other correction state, which I will call phi 2. Okay? Clear? So I'm just expanding these states as a function of lambda into a power series in lambda. Okay? Here and there. And similarly, the energy, I will write this as En 0 for lambda equals 0. I know I have the unperturbed eigenvalues, plus lambda, the first order correction, plus lambda square, the second order correction, plus, and so on and so forth. Okay? Notice these are corrections. Okay? So if I want the actual full number up to second order, I should include the 3. Okay? So up to second order, I should just include the 3 things. Okay? All right. So let us try to set up equations for all these quantities, which are obviously required to satisfy this equation. Okay? So for instance, if you plug into this thing, you will see immediately that you have what? H0 plus lambda V times phi 0n plus lambda phi 1n plus lambda square phi 2n. This plus other things should be equal to E0n plus lambda E1n plus lambda square E2n plus times, again an expansion for the state, plus lambda phi 1 plus lambda square phi 2 plus. Okay? I've inserted the expansion everywhere. And now I should look for equalities order by order. Okay? So for instance, let us start with 0 order in lambda. So things in which there is no lambda. Obviously here and here, there is no lambda. And this is the only thing on the side which has no lambda. And the only thing on this side that has no lambda is this. Okay? So obviously this I know, because this is the unperturbed problem that I started from. So H0 phi 0n is equal to, indeed, E0n phi n0. Okay? So there is no need to really. So the 0 order terms are happy, because I started from the unperturbed eigenvalues and eigenvectors. All right. Let us look to first order in lambda. You see that you will have a first order contribution from here. See, there is a lambda. And also from here, on this side. What about the right-hand side? I will have a first order contribution from here and a first order contribution from here. Okay? So let us write what this implies. And by the way, since there is a lambda everywhere, let's drop the lambda now. The lambda has done its purpose of signaling how many powers of lambda there are. There is only one. Let us drop it. And I should write, therefore, the following. So I have that H0 applied to phi 1, the first order correction, plus the perturbation applied to phi 0, the unperturbed state, should be equal to E1 multiplying phi 0 plus E0 multiplying phi 1. Okay? Now, let me rewrite this in a better way. You see that there is phi 1 here and here. Okay? So let me bring the phi 1 to the left and the phi 0 to the right. So I can write this as H0 minus E0n multiplying the phi 1 n. This should be equal to, or rather, let me write it plus with the plus V minus E1n multiplying phi 0 n should be equal to 0. Do we agree on this? Okay, I've just rewritten them all in the first thing. Now let us see something. For instance, notice if I take a scalar product here with, for instance, phi 0 n, obviously here and here, what happens? Can you see something? I can have this thing acting on the left, and since this is an eigenvector of H0 with eigenvalue exactly this drops, okay? So this is a trick to make phi 1 disappear. On the contrary, on the right, nothing really disappears, and this tells me immediately, so our first result is that the first correction in energy, n, okay, should be, since this is just 1, should be equal to the matrix element of the perturbation V between the original unperturbed state. Okay? So this is nothing but, remember, before I had, for instance, the E minus was equal to E0 1 plus lambda V11. Okay? So this is the V11, the same object. So the term linear in lambda is, by definition, what I call the perturbation E1. Okay? So this is nothing but that thing. By the way, let us copy back the two things so that we remember our exercise. Okay? And E plus equal to E02 plus lambda V22 plus lambda square V12 square divided by E02 minus E01. Okay? By the way, all I'm doing here assumes non-degenerate eigenvalues. Okay? So every time non-degenerate case. Okay? So is this clear until now? This was very simple. I just, but I can now do an even, still from this equation, suppose that I multiply by phi 0 m, where m is another state. Okay? So, since this is another state, okay, I have to put m here. This is still simple. This is equal to E0m minus E0n. Okay? Okay? So I can just rewrite now that for m different from n, I do have that E0m minus E0n times the m component of the first correction state plus, how do I write it? Plus like that. Plus phi 0 m v phi 0 n, okay, from here, minus E1n times what? Times a delta of n and m. All this should be 0, okay? This is what this equation is telling me if I multiply now by m. By the way, if I do the case m equal to n, I recover the previous result. So this drops, the delta is 1, and I get that this is equal to the matrix element in the diagonal, okay? So this equation is simply coming from this line if I put m equal to n. If I put m different from n, however, then this drops, and this allows me to solve for now the first correction to the state. After all, this was only the first correction to the energy. Now, this tells me that the first correction to the state, phi 1 n, his projection on the state m, generic m different from n, is equal to what? Is equal to minus phi 0 m v phi 0 n divided by the energy denominator that I can drop down here, because I know that I'm doing the non-degenerate case where these things are all different, okay? Notice if this were degenerate, then I wouldn't do this, because this might be 0 without really, even if they were different, okay? But they are non-degenerate, and therefore they are not 0. And I can solve, okay? So these are our first order perturbation theory result. It tells me what the new shift in energy is. It's just the diagonal element of the perturbation, as predicted here. And it adds a little bit more. It tells me also the correction to the eigenvector, okay? So the eigenvector gets, in general, a projection on every possible state, m, with a matrix element governing this projection, that is the matrix element of the V, divided by the energy difference between the two unperturbed eigenvalues, okay? So in general, the projection is going to be small on distant in energies eigenvectors, all right? Okay. So this is our first order perturbation theory result. Let us go to second order, and then we will stop, obviously. In principle, this is a systematic expansion, so you can go to any order you want, but you will see pretty soon that things become very cumbersome as you increase the order. So let us do second order. So the second order, let's see what the terms are. How do I get lambda square out of this products? Bah, for instance, I can get from here. I can get from here, okay? And that's it, right? Very good. Now, what about here? I can get now lambda square from three places, in fact. From here and that. From this and that. And even from this and that. Okay? You see there is a slight asymmetry between left-hand side and right-hand side. The reason is very simple. The left-hand side contains here lambda only up to power lambda. There is no lambda square here. On the contrary, while here there is an infinite expansion. On the contrary, on the right-hand side, everything has an infinite expansion. Therefore, there is also a lambda square correction here in principle, which is, however, missing there, just because it wasn't there in the Hamilton. Okay? You see, it's slightly asymmetrical, which is nothing really serious, but it makes the algebra slightly, okay? So let us see those terms. I have h0 times lambda square phi 2. By the way, lambda square is everywhere, so if I write just the coefficient of lambda square, I can drop it. So this is there. Then I have v times phi 1, which is there, okay? Then on the right-hand side, I have, for instance, let's see. I have phi 2, phi 0. Then I have E1 phi 1. And then I have still another piece that is E0 and times phi 2. Okay? So this is the equation to second order. Okay, so let's see. What do we know? Well, we know everything to order 0, so V0, phi 0 we know. But even everything to order 1. So we know this guy, okay, and this correction in energy. So the really unknown things are E2, for instance, and phi 2 next that I should determine. Okay? So I suggest you to do the following things. Let's rearrange the terms, and let's write here phi 2 with E0 minus H0, sorry, minus E0n. You see the last term there. Okay, let me bring it here. Phi 2n. Then I have first order terms, which are V minus, I bring this on this side, E1n times phi 1n. Okay? All this should be equal to here, E2n phi 0n. Okay? So let's see. Suppose that I take now the scalar product of this thing, usual trick as before, with phi 0n. Now, this has phi 0n, and this has also phi 0n, which is 1. So this immediately tells me, so let me write, where should I write? I think I can drop this part, right? Because you know the original case. Okay, so so E2n, okay, is on the right-hand side. Now this object here gives me E0n minus E0n. So again, drops. And this gives me what? Well, let's see. The constant E1, when I take the scalar product between phi 0, 1 and phi 0n, these two terms, you see, the phi 1 has correction only for m different from n. Okay? So what I have omitted from writing here is that I've taken essentially the n term to be 0. Okay? You can always do that. Okay. So you see that this term gives no contribution, while this gives me the following result: phi 0 n v phi 1 n. Okay? Very, very simple. You might say, hey, simple, but I have to insert this. Correct. Yes. Let us insert this object here. This is essentially what? Is the sum over m, you see. This is this object here. I can insert here a sum over m. So this is phi 0 n v phi 0 m phi 0 m phi 1 n, okay? And I know that this has only m different from n contributions, okay? And now I copy this result here, okay? And I put it there. So what I get is minus the sum over m different from n. Then I have this element, so phi 0 n v phi 0 m times this, okay? But you see that this is nothing but the star of that, okay? You see it's the m and n are exchanged. So I can write this as the modulus square, and then I have the denominator, which is E0m minus E0n, okay? This is a very important formula, okay? Probably one of the most important in this chapter of perturbation theory. So please try to kind of take due note of this thing. So the second order correction to the energy is minus a sum over all other states, not the one you are considering. So sum over all the other m different from n things with energy denominators like this, difference of energies, and the matrix element of V now between m and n squared. Now this should be no surprise to you. After all, we have already seen it there. Okay? It's the same thing. The plus or minus depends. If I am, for instance, have only two states, I realize that if I calculate the perturbation to the smaller state, then Em minus En is positive, and therefore that gets a shift down. On the contrary, if I am looking to the higher of the two, then Em minus En is negative, and it gets a shift up. Okay? So this is pretty general. Second order tends to push away the eigenvalues in two opposite directions. Okay? For a general case, obviously, if I'm perturbing and I'm looking for some level n, then there are many levels m both up and below in energy. So this sum is extended to all E0m up and below. So the sign of these things could be positive or negative. Okay? The sign of the numerator is always positive. And so you have to calculate balance of positive and negative term. Okay? And if the level is going up or down depends on the subtle balance of positive and negative corrections. Okay? For 2 is very, very simple. And this is also a way of keeping track of the signs. So if you want to remember if this sign is minus when you write it like this, always remember, if I have only two levels, the ground state is going to go down. Okay? So this will be positive, and this therefore has to be minus. All right? Is this clear? Okay. So this generalizes to the full non-degenerate case, the simple result of our first order. Okay? So we are essentially done with the general treatment of the non-degenerate case. In principle, I might proceed and calculate the second order correction of the state. You see, for first order, I first derive the eigenvalue and then the eigenvector correction. Here, I first derive the E02, and then I should derive the correction to this. But this is very, very seldom used in exercises, okay? So although in principle one might sit down and patiently write an expression for the second order correction, it's very, very seldom used. You see, this is simple. This is already more complicated, okay? So you expect that the second order correction to the state is a bit more complicated than this, okay? And is almost never encountered in practical calculation, okay? If one needs to really perform accurate calculations to higher order, one needs to set up a machinery that is a bit less cumbersome than this, okay? Although, in principle, this is a way. Okay, is this clear? All right, so let us do a few applications of this. So I will start now applying what we have just derived to a few exercises before doing the non-degenerate case. Sorry, the degenerate case. So the first exercise I want to do is in fact quite physical. Suppose that you have a charged oscillator, okay? So you are in one dimension. There is a spring, okay? So your H0 is obviously P squared over 2m plus 1/2 m omega square x square. So this is the spring. But this object has a certain charge, Q. And I put some electric field. In order not to confuse the electric field with the energies, I will use this calligraphic E for the electric field, okay? So an electric field generates a potential that is minus Q, the electric field, times X. In fact, if I take the derivative of this, I get the force. The force is just Q electric field. And therefore, the potential has to be minus Q electric field times X, okay? So before I had here just an harmonic potential, now I have harmonic plus linear term. And you realize that this is in general something like this. Okay? It's still a parabola, but shifted now from having a minimum in the origin to having a minimum somewhere else. All right? Okay? So the effect of an electric field indeed is not very complicated to treat exactly. Okay? We'll do now first the exercise exactly, and then we will use this as a perturbation and calculate our results in perturbation theory. All right? This is the plan. So let us first do things exactly. Well, you realize that this new potential can be written in the following way. For instance, where is the minimum? Well, to calculate the minimum, we have to take the derivative here and there. And you immediately see that the minimum is when m omega square times x is equal to Q electric field, right? Because this is the derivative equal to 0. So the new minimum here is for position Q electric field divided by m omega square. So a good idea is to rewrite this as x minus this minimum here, Q epsilon over m omega square. This is the new parabola in the shifted minimum. What do you think will be the coefficient here? Well, from the square term, I should obtain the original m omega square. So the coefficient here must be the same. Okay? Otherwise, I would not obtain from the square of x this term. Now, the linear term in x, you see, is just the right one. If you calculate the 2x minus 2x cubed times that, you just get this. You see this term cancels with that. The 2 cancels with that, and you get that. But this object here has an extra term that is second order in the electric field, okay, with a plus. And therefore, you have to subtract what you have improperly added, which is Q square electric field square divided by 2m omega square. Okay? So the full Hamiltonian, so this one, is also written as So H is equal to P square over 2m plus this. Is this clear? Now, why is this problem exactly solvable?
Because it's just translation, and then we add something which is just a number.
Just a number, right? So suppose that I work with the new variables. The new variable will be x prime equal to x minus q over m omega square. Now, being this a shift, okay, the new momentum will be just equal to the old one, okay? Because the derivatives with respect to x and with respect to x prime are identical. So I can rewrite the new Hamiltonian in these new variables, okay, as p prime square over 2m plus 1/2 m omega square x prime square. But there is this term, this extra constant term, okay? Now, the constant is not very important. It's some shift of all eigenvalues. But the problem itself is just identical to the usual harmonic oscillator, okay? So you know all the energies of these things, what they are. They are just n plus 1/2 h bar omega, obviously minus this overall constant. Okay? So you can just, if this were the original eigenvalues, they are just shifted down, if this is the thing, by, I mean, all the same thing, okay? So they are just shifted by a uniform constant. Is this clear? If I ask you the eigenstates, however, okay, for instance, let me ask you, what is the eigenstate associated to this problem at a certain electric field? Now tell me, well, very, very simple. It's the eigenstate of the harmonic oscillator, however, in the variable x minus that, okay? So what is it? It is psi 0 of x minus q epsilon over m omega square, okay? So this is not centered in 0. It's centered into this minimum, okay? So you perhaps discover that the famous displaced Gaussian of the midterm exam is nothing but the ground state of this oscillator in the presence of an electric field. All right? Okay? Good. So the states are all simple, but shifted with respect to the standard oscillator. Okay. So let us now calculate everything in perturbation theory. Okay. So perturbation theory to first order. What I should do is to take the perturbation, which is once again this, and calculate the matrix element. For instance, if I want to know the shift to first order in the perturbation, I should calculate the value of x, the operator x, between two states of the unperturbed oscillator, n and n, the same, okay? But you know that these eigenstates have a definite parity. They are even, odd, even, odd, even, odd, okay? If I try to calculate the expectation value of x between the same state, be it even or odd, it means what? It means an integral over x of x times the wave function, okay, squared. Square means even always, okay? So it's something that obviously has to be 0, okay? So this is 0 by parity. You see that in some sense, selection rules, symmetries help you to decide immediately without really calculating if a certain matrix element is 0 or not, okay? There is a chapter of the story that is called selection rules that is, in fact, something that we have to come back to, okay, before we end this discussion, because for parity is very simple, but sometimes angular momentum is more tricky and needs to be discussed, okay? So before I will need that, I will discuss again. Now, you immediately realize that this means that first order shifts to anything should be 0, which is reasonable. We discovered that the shift is all quadratic, so no first order. Okay, so let us calculate the second order shift, this formula. In order to do that, what we have to, let's see the ingredients. I have to calculate these things, and I know, because these are just difference in energies, the unperturbed energies, I know them. And I have to calculate matrix element of the perturbation, x, now between two different states. Within the same state, it's simple to conclude it should be 0. Between different states, might be different from 0, okay? Let's see how to calculate all these ingredients, okay? What can I erase? I think I can erase here. Okay. Now, again, the algebra of the A and A daggers is useful. In principle, I should calculate matrix element of x between Hermite polynomials multiplied by Gaussians. But if I do it, just straightforwardly, it's integrals that are kind of painful. Obviously, there are recursion formulas for Hermite polynomials that if I go and look in the books, I will find, and this will help in calculating those integrals. But luckily enough, we have a powerful tool to do the calculation. For instance, okay, let us see. This object here, remember, I have that x is equal to, well, 1 over square root a plus a dagger. Well, not quite. X, as it is written here, is the operator with dimensions, okay? So there is really L, okay, where L is the famous oscillator length, okay? So the thing that we calculated such that, if you remember, h bar square over twice the mass L square was equal to 1/2 m omega square L square, okay? So you can calculate again what L was. L square is the square root of h bar over m omega, if I remember well. Okay? So there is L. Huh? L without the square is a square root, like that. Huh? It's okay? Okay. Well, let me check 1 second, okay? I always believe only. So L to the 4th is equal to h square over m square omega square. So L square is that. Yes. Okay. Now I believe it. Okay. Good. I never remember by heart. Okay. You realize that this is. Okay. So now the other elements that I have to calculate are this, but I know that these are states. Okay. The famous states with a dagger to the power m applied to the ground state divided by square root of m factorial. And here I have similar object with n. The difference in energy, okay, in general is what? Is equal to, let's write it here, will be h bar omega then I have m minus n. The 1/2 cancel. Okay? So I think I basically know all the ingredients here. Okay, so let us calculate. X, so the perturbation V, V is really minus V is minus Q, the electric field X. So minus Q, the electric field L, okay? So this is explicitly the perturbation. So it has A plus A dagger. So acting on a certain state, for instance, let us write this like that. Maybe it's simpler. Okay? So if I am considering a certain state n, which I want to calculate the shift. Okay? So select a certain n. Now, with V, what I can do is to destroy an A or create an A dagger, which means that from n, I can go to n plus 1 or n minus 1. Okay? So there are two possible values only of this m. Okay? Although in principle I have a sum over all the m, in practice, the matrix element only couples m that are just n plus or minus 1. Okay? And by the way, if n is 0, the minus 1 is not possible, only the plus 1, obviously. Okay? But if n is positive, there is always both, two of them. Okay? So let us do the calculation. So what I have is right here, E2n equal to minus, okay, this term here for n equal to m equal to n plus 1, so minus, the denominator is, where is it? H bar omega, n plus 1 minus n, so essentially 1. The numerator is the square modulus, let me first write it, phi 0 n plus 1 v phi 0 n modulus square. Okay? And then in general I have also another term, this minus. This time the denominator will be h bar omega times minus 1, because now m is equal to n minus 1. And the matrix element I have upstairs is phi n minus 1 v phi n, okay, modulus square. So I should calculate those two numbers. Let us do it. So apart from factors, and the factors are this, okay, which I can take out, by the way, and they are common to both. Okay, so I write this as minus a factor that is q epsilon L over square root of 2 squared. Square because there's a modulus square there. Then I have sorry, let us write with the plus so that we keep all the signs there. So it's minus 1 over h bar omega. Then I have what? A plus A dagger. Well, only A dagger acts there, right? A dagger acting on n gives me the n plus 1. Do you remember with what coefficient? Huh? Square root of n plus 1, right? When you square, it's n plus 1. Okay? Nothing else, because the rest is dimension-full numbers that I have taken out. Okay, good. Then I have minus, and minus is a plus. There is still h bar omega in the denominator. And now I have A plus A dagger here. Well, I have to go down, so only A matters. A applied to phi n gives me square root of n. Square root of n. I square, I get n. You immediately see that I don't even need to distinguish the case n greater than the ground state from there, because if this is the ground state, this term is not there. You see, there is the matrix element takes care of killing it. Very good. Okay, so I do this calculation, and I see immediately that n really cancels from these two terms. And all I have is minus q square, epsilon square, L square divided by 2, and then I have h bar omega. Now, shall we put the formula for L square in? Yes, let's put minus q square, epsilon square, h bar over m omega. Then I have 2 h bar omega from here. You see that h bar actually goes away. And all I have is minus q square, epsilon square over twice m omega square. Completely classical, no h bar, and absolutely the exact result. Okay? You see, it doesn't depend on n. So the shift is equal for all. It's just the same, minus q square, epsilon square. Now, this teaches you that the second order calculation somehow captures exactly the shift of the energies. So there is no need to go to third order in the shifts and so on, okay? Although you shouldn't believe that second order is exact. Indeed, the energy eigenvalues are captured exactly to second order, but not the eigenfunctions, okay? The eigenfunction, you will see, even the ground state. The ground state is the Gaussian shifted. If you try to express this Gaussian shifted in terms of Gaussian, Hermite polynomials, everything unshifted, you will notice that all powers of epsilon of the electric field appears. Okay? This is very, very simple. Let me show you to you, and then we go. So I have C times e to the minus x minus q epsilon over m omega square divided by 1 over 2 L square. This is the new ground state. Okay? You see that I can square. I can rewrite this as C e to the minus 1/2 L x square. Then there is a constant term e to the minus 1 over 2 L square, the square of this. And then I have a term that is e to the minus, but there is a minus and minus, so e to the plus, what? The 2 and the 2 cancel, so 1 over L square x q epsilon over m omega square. This is still exact. Now I can expand. Forget about this. This is just coefficient in front. I can expand this, and I get 1 plus 1 over L square x q epsilon over m omega square plus the square of this plus the cube, and so on and so forth. So you see this is order epsilon, order square of the electric field, cube, and so on. Okay? So in general, I have all possible powers of the electric field there. And the first order formula, which is this, if you calculate, will give you only this piece. You see this x times the Gaussian is nothing but the first order Hermite polynomial times the Gaussian. So this is essentially the phi 1. So the formula correctly accounts for those things, okay? But certainly these things are not there, okay? They are obtained in second order perturbation theory to the state. These are obtained to third order perturbation theory to the state, okay? Although for the energies there is no need to calculate anything else. So a bit cautious in thinking that this is a very simple problem. Can be solved exactly. Second order perturbation theory for the energy is trivial, simple exercise exact, but don't think that the states they are all shifted, and the shift is not a trivial thing in some sense, okay? It involves all powers of the electric field, okay? I think that this is enough for today. Tomorrow we will do another, not tomorrow, next week, another perturbation of the oscillator, okay, with some quartic or cubic perturbation. Okay, so if there are questions, otherwise we are happy with that. Oh, yes, I give to you as an exercise to calculate from the formula we gave the corrections up to first order in the ground state of the harmonic oscillator, okay? And compare the approximate expression you get from here with the exact one that you have here, okay? So this is a kind of exercise that you should try to do. Yeah. These ones? These ones are the basis of the unperturbed solution. The phi1, phi2, and phi3 are what you have to add to that to get the solution up to first order, the solution up to second order, okay? No. No. The different elements of the basis are just given by different values of m. 0 means the basis. 1 means corrections to first order. 2 corrections to second order, but these are not states of this. So it's not an index of this m that appears there. Okay? Which one? This? No, it's, okay, let me try to repeat the idea. The basis is, in some sense, once and for all, that of the unperturbed potential. But now I say the n state, okay, lambda, starts being the unperturbed basis state, okay? But once I have a finite lambda, I have a small correction to that, which is some state, phi1, and to remind me that I'm perturbing n, I put an n here. It doesn't mean that, this will form a new basis. No, it's just a small perturbation to whatever was this, okay? Which I calculate by projecting, for instance, over all the basis elements with that formula, okay? Then there will be some other small correction to second order, okay, which I call phi2, and to remind me that I'm still counting for the n, I put an n there, okay? But these are just labels to remind me what I'm perturbing, okay? While this is also the label of the basis element of the unperturbed thing, which is therefore kind of, okay? Yeah. Which one? This one? This? Okay. Did you follow the expansion of the square of the Gaussian? Okay. So I took this exponential to the power x, and I expanded into 1 plus x plus a squared. Maybe if I write this as e to the a plus a dagger times something, okay, you realize that what you are doing here is to try to expand this into objects that have powers of a daggers and powers. The powers of a daggers are this, okay? The a in this case don't really matter if you apply them to to the ground state, okay? So this is what you did in the midterm, essentially, okay? So these powers reconstruct for you a dagger to the ground state, a dagger square, and so forth, okay? But, I mean, to simplify the answer, expand the exponential, and you will find all powers of x. Please, voice. To which one? This is exactly the exercise you have to do, okay? So you have to take this, which you know, expand to the appropriate powers of the electric field, and check that you get exactly this expression for the perturbation to the state. You see, this tells you the perturbation to the state, matrix element M, is given by a certain number, okay? You should calculate what the number is and check that it correctly matches with this thing, okay? I mean, maybe I was not clear enough, but I mean, x times this Gaussian x squared over 2L squared is the first order state. I mean, is, sorry, the phi1, 0. Okay? So, I mean, you will notice that essentially this couples 0 with 1 and gives you exactly a piece of this with the right coefficient. So please try to sit down and do the exercise, and you will discover many aspects of this formula that, if you simply look at the formula, are kind of abstract, okay?